Assalamu alaikum. Today we'll be discussing capacitors with dielectrics. This is article number 26.5. Sorry, I forgot to write it. Please write it down. It's article number 26.5. In this article, we'll be studying the effect of dielectrics when they will be introduced into a capacitor. We'll see whether the dielectric will increase the capacitance of the capacitor or will decrease it. Before going into detail, one thing which is of very importance over here is an insulator. इंसुलेटर हमें पता है क्या होता है. इंसुलेटर कोई भी ऐसा मटेरियल है थ्रू विच वी कैन नॉट कंडक्ट इलेक्ट्रिसिटी or it's not neither a good conductor of heat. So anything which does not conduct is an insulator. So insulator जो है उसमें जो पॉजिटिव और नेगेटिव चार्जेस हैं वो इस तरह से अरेंज होते हैं कि we don't have free electrons in an insulator. So when there is no free electrons, then it won't be able to conduct. But when we apply an external electric field to an insulator, तो क्या होता है कि हम उस इंसुलेटर के अंदर डायपोल इंड्यूस कर देते हैं. डायपोल्स क्या होते हैं? डायपोल्स भी हम चैप्टर नंबर 23 में पढ़ आए हैं, बट I'll explain a little bit over here. डायपोल्स वो होते हैं कि जब हमारे पास completely एक साइड पे नेगेटिव चार्ज आ जाए और एक साइड पे पॉजिटिव चार्ज आ जाए. That is, the charges they align themselves in such a way that on one side we have negative charge and on the other side we have positive charge, and they are separated by a certain distance. So हम कहते हैं कि we have created a dipole over here. So electric field, whenever it is applied to an insulator, it induces dipoles in it. So जब हम कभी इलेक्ट्रिक फील्ड अप्लाई करेंगे तो हमारे पास क्या होगा कि when this field is applied to an atom, this atom was spherical in shape before the application of external electric field. The moment I applied this electric field, this spherical shape becomes a little bit elongated, and the positive charge and the negative charge, they shift themselves in such a way that on the upper sides we have negative charge and on the lower side we have positive charge. Because of the direction of the field, we know that when the field is in this direction, it means that it is originating from positive and moving towards the negative. So if positive is over here, then the electrons, they will align themselves near to the positive charge, and if positive is over here, then this positive this has aligned itself because of the presence of negative charges over here. So जब हमने फील्ड अप्लाई कर दी तो इस फील्ड की एप्लीकेशन के बाद ये स्फेरिकल एटम जो है ये अब थोड़ा एलोंगेटेड सॉर्ट हो जाएगा और एक तरफ सारा का सारा नेगेटिव चार्ज हो जाएगा और दूसरी तरफ सारा का सारा पॉजिटिव चार्ज जो है वो हमें नज़र आना शुरू हो जाएगा. I'll simply read the lines just to make sure कि तुम लोगों को ये चीज़ क्लियर होगी है. It happens that they will start spending a little bit more time on the upper side, the negative charges, because the positive charge is over there, and the positive charges, they will spend a little more time in the at the lower side because we have negative charges over here. So इस तरह से हमारे पास अब डायपोल जो है वो बन गया है, क्योंकि एक तरफ सारा का सारा पॉजिटिव है और दूसरी तरफ सारा का सारा नेगेटिव चार्ज आ गया है, और अब वी हैव क्रिएटेड अ डायपोल in an insulator. So अब this figure explains it a little bit more. This is originally an insulator is, that is all the positives, and the circle, this circle, this represents the positive charge and the negative sign represents the negative charge. So before the application of electric field, the insulator looks a bit more like this. There are no free electrons, and we cannot see a dipole. All the electrons and the positive charges, they are fixed in such a way that we cannot have free electrons over here. But after the application of electric field, you'll see that this negative line has shifted up, that is towards the positive side of the field, and leaving behind, this is the layer of the negative charge which has moved up towards the positive field, leaving behind this positive charge. Now these electrons will shift to this layer, and then this to this layer, and we'll have a whole line of positive charges left alone at the bottom over here. So this is how I can say that I have created a dipole over here. That is, this all the negative charges, these negative charges will spend a little more time over here towards the positive side of the field, and these positive charges, they will spend more time over here, that is towards the negative side of the field. Okay, so when I have this figure B, I'll call it that I have done the process of polarization, uh, because I have polarized the charges, that is, I have created a layer of negative charges over here and a layer of positive charges over here. So polarization has taken place, and the substance in which I have done this polarization is now known as a dielectrics. There are different types of dielectrics. Some are permanent dielectrics, and in some insulators I can induce polarization and can make them useful as a dielectric material. So now this dielectric will play a very important role in capacitors. So now coming on to capacitors. Suppose I have a parallel plate capacitor. I charge this parallel plate capacitor with some external source. I have applied certain potential to these plates, and I have charged them in such a way that the upper plate gets all the positive charge and the lower plate gets all the negative charge. So the charge density on this plate will be plus sigma, and the charge density on the lower plate will be minus sigma. So and the distance between the plates will be d. As the upper plate is positive and the lower plate is negative, so the direction of the field in this case be from top to bottom. So now I know that d is the distance between the plates, positive charge is the charge density, negative charge is the negative charge density, and E is electric field. Area of the plate will be given by capital A. So now after I have charged these plates, I remove the potential, and now the charge is trapped on these plates. So now there is no external source to charge them. I have made a parallel plate capacitor, and now what I'll do is that I'll introduce a dielectric material within these plates. So when I introduce a dielectric material in these plates. So naturally, because the positive charge, they are present on this plate, so after the introduction of the dielectric material within these plates, the polarization process, it will take place in the dielectric. All the negative charge, they will shift. This layer of negative charge is for the dielectric I have introduced within the capacitor. So all the negative charges, they will align towards the positive plate of the capacitor, and all the positive charges, they will align towards the negative plate of the capacitor. And I'll call the charge density on the dielectric on this surface be sigma naught, and this is the induced charge density, and there I'll be getting sigma naught. I think this will be minus and this will be plus. So now within the dielectric, I have all the positive charges over here and all the negative charges over here. So the induced electric field will be in the opposite direction to that of the electric field already present within the capacitor. So it will be in the opposite direction, that is from bottom to top. Now, everyone, please keep this figure in your mind, or you can draw this figure on your notebooks, because आगे अब इसकी इक्वेशंस जो हैं वो हम सॉल्व करेंगे, तो उसके लिए थोड़ा सा ये फिगर अगर आपके साथ हो तो वो बेहतर है. मैंने आगे ड्रॉ नहीं की हुई, so यहाँ पे again I'll try to draw it. We have a parallel plate capacitor जिसका जो है this is positive, this is negative, or we have an induced layer of negative charge over here and an induced layer of positive charges over here. The direction of the electric field originally जो थी वो ये थी, और then because of the induced charges वो हमारे पास ये आ गई. So this was sigma and sigma, and this was sigma not negative, and this is sigma not positive, and this will be E naught, and this is E, and the distance between the plates is D, and the area of the plate is A. So now from our previous knowledge, we know that electric field, when we have two parallel plates, the electric field is given by sigma over epsilon. Epsilon is permittivity of free space, so it's a constant. And for E naught, we may write sigma naught over epsilon naught. Now the net electric field is the vectorial sum of both the fields. Obviously, अब net electric field क्या होगी इस पूरे की पूरे figure में? It will be the sum of E plus E naught. I can see that the direction of E is this and the direction of E naught is in the upward direction. So obviously, I can write this as this. The E net will be E minus E naught. Now we will assume that fraction of the free charge is induced. So it is assumed that sigma induced, that is sigma naught, is some fraction time of sigma. So sigma naught जो है वो ये b is some fraction, और इसका सिग्मा का मल्टीपल है इस b के साथ, and this b is always less than 1. So please remember that whatever the fraction we are choosing to multiply with this sigma, it has to be less than 1. So sigma naught is equal to b sigma. Now this is one important equation. ये आगे जाके हमें जो है डाइलेक्ट्रिक कांस्टेंट की वैल्यू निकालने में हेल्प करेगी. So now if this is the case, if this is the case, obviously हमारे पास चूंकि वैल्यू ऑफ E जो ऊपर थी हमने देखी कि E is equal to sigma over epsilon naught. So अगर and E naught is equal to sigma naught over epsilon naught. So if I have this, so I can easily write that E naught is equal to dE. So only replacing sigma naught with B sigma. So when I replace E naught equals to B sigma over epsilon naught. So I know that this sigma over epsilon naught is equal to E. So I have written E naught is equal to BE. So now I have the relationship between the induced electric field and the electric field already present in the capacitor. So easily we can see that these two are connected to one another. So now I can replace this E naught in this E net, which I have written before. So E net is equal to E minus BE. I can take this E common and I can write this 1 minus B. Now this 1 minus B is equal to 1 over kappa, and this kappa is known as the dielectric constant. So dielectric constant is a dimensionless number, and it plays a very major role in the selection of dielectric within the capacitor. Every material has its own dielectric constant number. So these are known numbers. Kappa is known number. So in general, now we can write E net is equal to E over kappa. So I have this E into 1 minus B, where 1 minus B is equal to 1 over kappa. So I can write this E over kappa. So net E is equal to E over kappa, which means that the net field is reduced when a dielectric is introduced within the capacitor. Now if E goes down, then it is clear that the potential difference will also go down, because we have V equals to ED. So if E is going down, this means that V will also go down. Now if I keep this D constant and E is decreasing in its value, so obviously V will also decrease because they are dependent upon one another. Now to check the validity of Gauss's law, because um, it has to be valid over here. So we know that the Gauss's law is closed integral E dot dA equals to 1 over epsilon total charge, that is for all charges. So in this case we will consider the positive plate and the induced charges, that is the negative induced charges near this positive plate. So this will be a closed surface. So considering the upper plate where we have positive charges and the induced charges, they are negative. So this is the Gaussian surface we are considering right now. So taking this into account, we can write the equation that closed surface integral E dot dA equals to 1 over epsilon summation q over kappa. So from here we know that yes, the Gauss's law, it does hold in this case. So again, now coming back to the fact that if we have an external field and we apply that external field to an insulator, we induce dipoles in a molecule, but some substance are there which themselves already have dipoles in them. So if an external field is applied to these dipoles, they will start to align themselves. But make sure that the temperature does not go very high, because the temperature then plays a negative role over here and will try to disalign the charges, and we won't be getting a strong induced layer of charges over there. So if the strength is required, then the temperature must stay down, otherwise it will play a negative role over here. There are some materials, as I have already told you, they are permanent dipoles and are much stronger than the ordinary dipoles. Water is a permanent dipole molecule. The value of kappa of water is 80, and when it is in the form of ice, it is 100. So again, you see that when it is at a greater temperature, the value of kappa is 80, but when it is at less temperature, that is close to 0 degrees Celsius or less, then it is 100 kappa. So this again shows that the temperature plays a negative role in dielectrics. So now we'll see what happens to the capacitance. We know that capacitance is C equals to Q over V, as we have seen that by introducing a dielectric, E and V goes down. So if E and V goes down in the formula, we can see that C is equal to Q over V. If V is going down, then obviously C will go up. So it means that if we introduce a dielectric in a capacitor, it will increase the capacitance of the capacitor. So remember this formula we have used for parallel plate capacitor to calculate its capacitance. We know that for the parallel plate capacitor, C is equal to A, which is the area of the plate, epsilon naught constant over D, separation of the plate, into kappa. So it is when the dielectric is being placed within the capacitor. So uh, again, you have to remember these equations we have gone through before. E is equal to sigma over epsilon naught, kappa V is equal to Ed, and this so it will help you in writing the formula for the capacitance. So now actually what happens to the capacitance is, again we have this C is equal to Q over V. We know that E is equal to VD. So if E remains constant, so it means that there is no change in E. So E is equal to VD, and if E is constant, then V into D is constant, as we are not changing the distance between the plates. So the charge on the capacitor uh, is because of the increase of the charge on the plate. So we can see that C is equal to A epsilon naught over D into kappa, and we can write C equals to A epsilon naught over D into kappa. Now this equation clearly shows that by introduction of a dielectric material within a capacitor will increase its capacitance by a factor of kappa. Whatever material will be using, it will affect the capacitance of the capacitor. Although the value of water and ice, it's too large, but the problem is that their breakdown field is very low. So obviously at some temperature the molecules, they'll start breaking. So we cannot use water or ice as a dielectric material. And secondly, mostly air, and then mica sheets and glass, they are used as dielectric materials to increase the capacitance of the capacitor.